Hi, my name is Artem. I am a research engineer at Moscow Institute of Physics and Technology. Today, I would like to talk about the IGLU competition, which was accepted at competition track of NeurIPS 2021. This competition is organized in collaboration with Microsoft Research, University of Amsterdam, Moscow Institute of Physics and Technology, and Facebook AI Research. Today, I will briefly go through a general introduction to IGLU competition. I will go through details on tasks, reinforcement learning environment, baselines we made, and how we will evaluate your solution. Finally, you will see how do we collect the data which would enable learning from demonstrations. First of all, we know that humans can acquire new skills quite quickly through natural language interaction with each other. They can ask clarifying questions, they can provide feedback, thus reducing the experience needed to learn something new. On the other hand, artificial agents are mostly trained by trials and errors for using reinforcement learning, for example, or by demonstrations. This motivates us to enable grounded natural language understanding, which means to build agents that are capable of participating in dialogues with humans and assisting them to complete some real-world collaborative tasks. This can be achieved by bringing together two research fields that usually stand out from each other, namely natural language understanding and reinforcement learning. For our competition, the main platform will be Minecraft. Minecraft is an extremely popular game with over 200 million copies sold. Minecraft has rather simple 3D voxel world with quite simple and predictable rules. Also, Minecraft enabled dialogue interactions with players. So all of that allows people to study and assist each other in Minecraft. Also, there are already a number of AI platforms in Minecraft. For example, Malmo, which is simply a Minecraft mod. Malmo is an AI experimentation platform. It provides a set of general interfaces which allows to train agents in Minecraft. Other example is Craft Assist and DroidLab, which are frameworks for also for building intelligent agents in Minecraft, but with emphasis on dialogues. There is also a number of reinforcement learning competition in Minecraft. For example, Marlo, which is a multi-agent reinforcement learning in Minecraft, or Mineral, which focuses primarily on sample efficiency in Minecraft. Before I proceed to the tasks, let me briefly describe our overall goal in the following example. This example was taken from the collaborative dialogue dataset in Minecraft from the recently published paper. In this task, there was two players, architect and builder. The goal of the architect was to generate proper step instructions for the builder, given access to the target structure and what the builder has recently done. The goal of the builder was to properly build the target structure inside the building zone, possibly asking clarifying questions in the chat. The only interaction between architect and builder occurs in the chat, and the builder, of course, hasn't access to the target structure. So this motivates us to ask the following research questions: how to build interactive agents that learn to solve the task while provided with grounded natural language instructions in collaborative environment. In our case, collaborative environment means that there are two players where one teaches and other learns. And this leads to two research questions. First one is how to teach. This research question obviously leads to the architect task. The second question is how to learn. We further subdivide this question into two sub-questions. First one is how is silent builder able to learn? And second one, how is interactive builder able to learn? These two questions poses silent builder task and interactive builder task respectively. The only difference between these two is that silent builder cannot ask clarifying questions and interactive builder can. So to be formal, we will have three tasks. In the architect task, your goal would be given target structure to generate step instruction for the builder. This instruction should be neither too specific nor too general. You should explain the goal unambiguously. And this task is obviously a conditional text generation problem, which involves both language and visual understanding. The second task is somewhat intermediate task on the way to the purely interactive agent. Our vision is that this is a pure RL problem where you will need to train a goal condition policy where the goal is represented by a chat between the architect and builder. Each chat will be obviously taken from the dataset, which I describe later. The last task is the interactive builder task, and it is the most challenging task in our competition. This is the place where interaction between reinforcement learning and natural language understanding would really happen. So the heart of our competition is the dataset. We collect the data with collaborative interaction and use it primarily for evaluation. We will have two stages of evaluation, offline and online. During offline, we will automatically measure some metrics on our collected data with your model. And during online, we will pair a human evaluator to assess your model. So by the beginning of the competition, we will publish some starting code, reinforced learning environment, and dataset for training from demonstrations. That's it. So for each task, we will have two stages of evaluation. For the architect task, during offline evaluation, we will measure BLU score, precision, and recall on domain-specific keywords. And during online evaluation, we will pair your trained builder with trained architect, with human builder, and that builder will interact with your model and rate it quality. For silent builder task, during the offline evaluation, we will do the similar thing, namely measure episode reward, success rate, etc. And during online evaluation, we will pair human architect, which will instruct your builder and rate it quality. As for the interactive builder task, we will have only offline evaluation stage, where we'll measure the same metrics as for the silent builder. So we plan to launch our competition on 2nd of July, where you will have approximately 90 days to train, submit, score, repeat all of that with your model. And after that, we will select top 3 solutions per team per task and proceed to the next stage, during which we will perform the human in the loop evaluation. We will assess all of that models and name the winners. So let's dive into the details about our tasks and baselines. First one is the architect task. For this task, we actually built a simple baseline, which is a sec-to-sec RNN model, which is conditioned on 2 vectors. First one is the representation vector of current conversation of builder and architect, obtained from RNN. And the second one is the world state representation vector. The world state representation vector consists of 2 parts, the global block counters and the local block counters. We encode the information about currently built structure and the target structure into the global block counters, while the local block counters represent local information about the surroundings around the builder's head. This second component allows the model to reason locally about what the builder should do. These 2 vectors are passed to the decoder, which generates output utterance, which goes through to the builder. So as I said, for evaluation, we will use BLU score and precision with recall on domain-specific keywords. We actually have trained this model on Minecraft dialog dataset and made an evaluation. We see that obviously these 2 components, namely global and local counters, increases the scores of the model in almost all of the metrics compared to the vanilla sec-to-sec. This is quite a simple model. Of course, we'll update it by the beginning of the competition with something more advanced and recent. So let's talk about the reinforcement learning part of our competition. As I said, in the silent builder task, your goal is to train a model which can build target structures given human instructions. The agent acts in first-person environment with the ability to place, break, and select blocks of different types. In the images below, you can see the examples of actual observation from our environment with some target structures. For example, this structure is called a broken heart. Of course, the agent will start from the empty build zone. So these are just examples for your information. Currently, we are collecting the data set for use as demonstration for RL agent. This data set will be filled with architect builder interactions. So let's look under the hood of our environment. When you reset the end, you obtain the observation. First component of our observation space is the image. This is an 64 by 64 RGB first-person image. The next component is the inverter state. The agent has 20 blocks of each of 6 types. Also, the agent has access to the chat between the builder and the architect. For your convenience, we also expose 2 additional components of the observation space, the agent position and grid wall state. These 2 components are just for your learning because we will not expose them to the agent during the evaluation of your model. So you can just play with these simple cases and then proceed to the more advanced case when your agent can only access to the images. As for the action space, we will have movement actions, which stands for just forward, backward, left, right, and jump. Camera movement, which is a two-dimensional continuous control vector. Actions for placing, breaking blocks, and action for selecting blocks of different types. Probably the most important thing in RL is rewards. Therefore, we put a lot of efforts on making the rewards suitable. When we first tried to train agents, we observed that agents barely can learn anything. Even in the simplest case, when agent was forced to place just one block correctly, the agent failed. This was primarily due to the fact that agent was forced to learn where to build rather than what to build. For example, if you have target structure like this, sort of L-shaped structure, and the agent has built the same structure but in the wrong place, with naive rewards, the agent will get all negative rewards despite the agent was successful. By naive rewards, I mean that we compare target structure and target zone and builded zone as is and calculate the per block intersection between them. So therefore, we decided to bring the invariance to the placement into our reward function. Unfortunately, this introduces a bias into the training, but on the other hand, it makes the task more accessible for our RL agent. Despite we cannot debias the reward, we actually can debias the data. For example, the architect should instruct the builder, for example, to place the structure anywhere he wants. So let's see how we bring invariant to the placement into our reward function. First of all, we compare all relative translations and rotations around vertical axis of goal zone and building zone. Then we calculate the size of maximal intersections among all these translations and rotations. For example, if we have a target structure like this, as in the previous slide, and the agent has built 2 diagonal blocks, if you would consider this pair of translation and rotation, we will see that the agent actually completes the task by a half, and the target structure fully covers the build one. So to calculate the reward using the maximal intersection size, we compare that with the one on the previous step. For example, if the maximal intersection size hasn't changed, we reward the agent with -1 if the agent places a block, or with +1 if the agent removes a block, or with 0 otherwise. If maximal intersection size is increased, we reward the agent with +2, or if the maximal intersection size has decreased, we reward agent with -2. Actually, this reward function is quite costly to compute. Therefore, we used a bunch of heuristics to accelerate the reward computation. When you train the reinforcement learning agent, you'll probably need to do reset operation on your environment. In all Minecraft competition, the environment reloads the whole mission during the reset operation. This corresponds to pressing the escape button, exiting to main menu, reloading the game when the whole world is being regenerated from scratch. This operation takes around 10 seconds, which is a lot for reinforcement learning. Happily, our world consists of unbreakable ground blocks and the blocks placed by the builder. We can remove the builder blocks programmatically, teleport the builder, fill its inventory with initial state, and here it is, we reset the end. We call this operation a fake reset. It costs us just one environment step. We hope this feature will help the participants to accelerate their research towards the solution. So let's talk about the baselines for RL part of our competition. As preliminary baselines, we trained simple reinforcement learning algorithms to test if our environment is even solvable by the RL agent. We trained the agents on the simplest goal, which was a blue L-shaped structure of 5 blocks. The observation space of an agent was position of the agent and the grid wall state. The action space was discretized version of the action space described earlier, particularly one hot discretized version. We trained a proximal policy optimization and prioritized dual and DQN from RL as two representative algorithms solving the task. What we observed was that both policies converge to episode reward of 6, which corresponds to just 3 blocks placed correctly, which is very suboptimal to us. And the good story that when we tried a different backend, by backend we mean a thing between wrappers and Minecraft client. When we tried a MineRL backend instead of Malmo backend, we observed that the agent converged to best possible episode reward of 10, which corresponds to the whole structure built correctly. So one may ask, why is it so? Because MineRL is actually on top of Malmo, so why is it so? Well, actually in Malmo, there is a different types of action spaces, for example, continuous actions, discrete actions, and human level actions for continuous, discrete, and human level control, I suppose. And the problem with continuous action is that when you do action, the actual action would occur in your environment like after 5 or 6 frames, which is really bad. So you tell your agent to go forward, and just in 5 or 6 frames it start going forward. This was the reason why the such powerful algorithms as PPO and prioritized DQN converge to such suboptimal solution. This was the reason. So having this task solved, we try to we are currently trying to build something more powerful. And what we first observed was that the agents start to fail very soon with the increasing structure of the with the increasing complexity of the structure. So instead of using the naive approach, when we provide the policy with the goal expressed as architect builder conversation taken from the data set, we split this task into 2 subtasks. First is to map the architect builder conversation to the target grid world, just to predict what the builder has to build in like in voxel space. We can train this model obviously from the data set, takes like some pre-trained transformer, fine-tuned head, just the default thing which we do in NLP. And the important thing that for RL training, we got rid from the natural language goals. We can use the artificial goals, the artificially generated goals represented as target grid worlds. So we can try training the policy using the random goals, and importantly, we can progressively increase the difficulty of that randomly generated goals. And this baseline we are currently working on now. We plan to publish it by the start of the competition. A few words about the evaluation protocol. So we will use the same metrics for both offline and online evaluation, as I said. Important thing, I mentioned that earlier, but I will remind you that the observation space will be only the first person observation, chat, and inventory. So these 2 observations, agent position and grid wall states are exposed only for your like toy experiments. For like production experiments, you have to deal only with that parts of environment. For measuring the performance of silent builder engines, we will measure the success rate, which is a fraction of fully built structures. We will measure completion rate, which is the size of built structure divided by divided by the size of the whole target structure, average over all target structures. Also, we will measure the average episode reward, which is a compound metric expressing the how fully the agent builds the target structure, how many wasteful blocks it places, and so on and so on. So let's proceed to the data collection part of our competition. So you may ask, what's wrong with Minecraft dialog dataset? It looks good. Why not to just take it and use it? So for the architect task, we can do this, and we did this because it contains all necessary information for the architect task. But unfortunately, it doesn't contain all necessary information for the builder task, because this is the actual action recorded from this data set, because the authors didn't aim on the reinforcement learning during the data collection. For example, like builder puts down 5 orange blocks. This is the actual action of the builder, which is obviously too abstract for our case. So now I will describe our data collection considerations. So why, again, why to collect the data? First of all, we want to have a separate set of tasks which will be hidden from the participants, obviously, to make offline evaluation of agents and architects, and also to enable the reinforcement learning from demonstrations. Our main priorities, as I said, as you may guess from the previous slide, is the data quality. We put a lot of efforts on the data quality. So here is our data collection platform. We will use some sort of crowdsourcing platform, for example, Amazon Mechanical Turk. In this platform, the human workers will go to the platform, and the MTurk will pair them, forming architect and builder. When they're formed, they just play Minecraft, one worker as architect, as I said, and one as a builder. But it's not an actual Minecraft, it's some sort of fake Minecraft written in CraftAssist framework, with CraftAssist framework. The CraftAssist framework is actually talking to some sort of fake Minecraft server, and the CraftAssist output logs. Logs contain conversations and builders actions. We have an adapter which transforms the builder's actions to the some sort of format which are compatible with our environment, and our environment just consumes that actions, forming tuples of actions, observations, and rewards, and all of this goes to some storage, forming the dataset. So here is how our data collection platform works. So you may ask, why don't you collect the data by yourself? That's a fair question, and we highlight two main reasons for the answer. First of all, we cannot just play Minecraft to collect the data, because our task is by an order of magnitude harder than those of MineRL. We put a lot of restrictions on what can be and what cannot be in our data. So if we would go through manual data collection, it would consume a lot of time. That was reason one. And reason two, the data collection is, we plan to adapt data collection tool to make human evaluation at stage 2 of our competition. So the two reasons. What do we especially take into account during the data collection? First of all, architect should instruct the builder, like if the architect would sit on the builder's shoulder and instruct it. Therefore, the left of the architect should be the same for the left of the builder. Another thing is what I mentioned earlier, the architect's instruction should be invariant to the placement of the target structure. There is also a lot of small considerations, which I will not mention now. And the second important thing is that the demonstrations from the dataset should follow the same environment dynamics as does our environment do. So as I mentioned earlier, after the end of the competition, of stage 1 of the competition, we will evaluate the best agents with human-in-the-loop evaluation. For example, for architect task, we will pair human builders to assess performance of trained architect by building structures. Human builders will rate plausibility and correctness of each instructions provided by architect. For the silent builder task, human architects will be paired with trained builders to assess performance of that builders. So the last task of our competition is the interactive builder task. This is actually the place where interaction between reinforcement learning and natural language processing would really happen. To our vision, it is the union of previous two tasks, because to train interactive builder, you have to have trained architect model which performs reasonably well. For baseline, we slightly modify the structure of silent builder. Namely, we add an auxiliary action, which is a dialog action. Once selected, this action enables the conditional language model, which takes a whole state representation as input, as condition, and generates the question. After that, we launch the architect model, which takes architect view and the whole state representation as input and generate the answer for that question. Once the question and the answer are generated, we add them to the dialog and the process repeat. Of course, on the next step, the dialog action would not necessarily be selected. We are happy to announce that all registered participants will be granted with compute power to train their models from Microsoft. Also, that we will provide a mentorship and discussion platform like Stack Overflow, but for our competition. So for all news, updates, and links, please stay tuned to our Twitter account, IGLU Contest, or our website, iglucontest.net. So I would like to thank the whole IGLU team from Microsoft Research, University of Amsterdam, team from Moscow Institute of Physics and Technology, and from Facebook AI Research. Without all of you, this competition wouldn't be possible. So thank you everyone very much and see you in July.